Hello, Papio South Honors Pre-Calculus students. This is Ms. Cronky with a video from Chapter 1, Section 6, all about piecewise functions. The general idea of a piecewise function is it's a function created by piecing together different parts of different functions. And generally you would have two or more functions to create a piecewise function. The notation for piecewise function looks something like this. So you've got that f of x or y equals, and then you have a large bracket, and listed in that bracket are different functions. So we're looking at the function negative 1/2 x minus 6, and you might recognize that to be a linear function. And we also have the function x plus 5, also linear. Okay. Now there's something extra on each of these functions, and they are sort of, you could think about them as restrictions to the domain. So when do we graph negative 1/2 x minus 6? Whenever x is less than or equal to negative 4. When should we graph x plus 5? Whenever x is greater than negative 4. We're going to do some graphing here in just a minute, and we'll be making some t-charts or tables of values. But just to kind of give you an idea of how this works, if I were asking you to evaluate this function, this piecewise function at f of 0, you would look at your x value, which is 0, and say, is that 0 less than or equal to negative 4 or greater than negative 4? Well, 0 is greater than negative 4, so we would use the second function, x plus 5, and do 0 plus 5, say that's equal to 5. So now we know the point 0.05 is on our graph. If I were to change my x value and do something like f of negative 10, then I would look back at those two intervals and decide negative 10 is less than or equal to negative 4. So I would use the first equation underlined in red, and I would do negative 1/2 times negative 10 minus 6. That's negative 1/2, or sorry, negative 1/2 times negative 10 is positive 5. 5 minus 6 is negative 1. So now the value for the function at negative 10 is negative 1. So we're going to use that idea of how we would evaluate a piecewise function to help us actually make the graph of a piecewise function. So I'm using the same piecewise function that you saw in the previous slide, and I am going to graph the function. In order to do this, again, I'm going to focus mainly on the functions first. So they're both linear functions. I know that they're going to look like lines, but I'm going to take one at a time, and I'm going to think about the domain, or the acceptable x's for that particular function. So I'm going to start with negative 1/2 x minus 6. I'm going to create a t-chart or table of values for it. And the highest value that I can use is negative 4. So I'm going to go ahead and put that on. It's kind of like a boundary point. Because it has the or equals to on this particular function, I know that that's going to be a closed circle or closed dot, closed point on my graph. And then because I can use that for all x's that are less than or equal to 4, I'm going to choose a value of x that's also less than 4. And maybe I'll just use negative 10 from the previous slide, but I could certainly use negative 5, negative 6, negative 7. I might choose something even because I have to multiply it by negative 1/2. So plug in negative 4. Negative 1/2 times negative 4 is positive 2. Positive 2 minus 6 is negative 4. And we already did negative 10 on the previous slide, and we got negative 1. Okay, so I can plot those 2 points. Remember, these are both closed points. So negative 4, negative 4. I've got to make a table of values, or not a table of values, but a coordinate plane here. Okay, go right about here. And so I'm going to go negative 4, left 4, and down 4. And that can be a closed circle. And then negative 10, negative 1, so 10 to the left and 1 down. Okay, that's another point on my line. And then I can connect the two dots, but I make sure that I don't extend my line beyond x equals negative 4. So it doesn't go beyond that point, so it's kind of like a boundary dot, and so it only goes to the left. So that's one piece of my piecewise function. The other piece of the piecewise function comes from the second equation, x plus 5. So I'll make a new t-chart, and this time I'm going to choose values where x is greater than -4. Now, something that's a little bit different here is that even though -4 doesn't work for this function, it's going to give us an open circle for that particular line. So even though it doesn't work, I'm going to put it into my table because it will serve as a boundary. I'll mark it with an open circle on the graph, and it will help me know like how far my line extends. So I am going to plug -4 into that, and then actually I'm going to move that -4 down because I can only use this when x is greater than -4. So I'm going to choose some value that is greater than -4, and I think on the previous slide we already did 0. So we know 0 is 5, and if I plug -4 in, -4 plus 5 is 1, I can mark those 2 points. 0, 5 is actually a point, so y-intercept at that line, and it's greater than -4, so it's going to be a closed circle on the graph. But remember, when x is equal to -4, this doesn't actually work for this graph. So when I plot that point, -4, 1, that should be an open circle. So I'm going to go left 4 and then up 1 with an open circle there, and then I can extend my line all the way to the right. Now, you should be able to look at your piecewise function and see that it would still pass the vertical line test. And the key spot where we're checking that vertical line test would be sort of at that boundary at x equals -4. Okay, notice because I have one closed circle and one open circle, it still fits the definition of a function. That's my piecewise function there. On a side note, you could still do domain and range for a piecewise function. If we were looking at domain and range here, looks like the red line is going to extend all the way to the left, so that would be -infinity. The green line is going to extend all the way to the right, which would be +infinity. And because one drops off at -4, the other one picks up right after that, there are no gaps in the graph, so domain would be -infinity to +infinity. For range, usually for line, because one side is rising and one side is falling, your range would be all real numbers. But in this case, we have one line that's falling, one line that's rising, and we're not using the entire lines for either. So we actually have a minimum point here at this point, -4, -4. So that would be the lowest value of my range, -4 inclusive, so I'd use a bracket. And then both are extending towards +infinity on the end behaviors there. So -4 to infinity would be my range. So just as we can analyze the other functions that we're used to, we can also analyze piecewise functions. Now let's try one other example. And this is an example where we've got not just linear functions. Notice there is a quadratic there, and then instead of 2, we have 3. So that just means that instead of 2 t-tables, we're going to need 3 t-tables. I try to make a mental note of what each function should look like as I look at the problem. That just gives me an idea, like when I'm looking at my graph, okay, that actually looks like a line, so that's right. So I've got f of x equals x plus 1, which I know is going to be a line. I'm going to go ahead and make my t-table for that. This I can use whenever x is less than 0. Remember that even though 0 is not included there, I'm going to put 0 in my t-table, but I know that this has to be an open circle on the graph, okay, because it's not or equals to, it's going to be open. And then it works for any x's that are less than 0, so I could choose -1. Plug those things in. 0 plus 1 is 1, -1 plus 1 is 0, and then I can mark those on my graph. So I'll go ahead and make a graph. That was pretty terrible. So I would go left or right 0, and then up 1. Oh, and that should be an open circle, so I gotta change that. Okay, that's my boundary. And then I would go left 1 and up or down nothing. That's going to be a closed circle. Because x plus 1 works for all x's that are less than 0, I can go ahead and extend that graph. I'm going to put that in red so that you can see that's that part of the graph. Next up is a function x minus 2 squared, which I recognize to be quadratic. So I'm thinking about what I know about quadratic functions, and that's that they are parabolas. This is good for any x's that are greater than or equal to 0, but also less than 3. So this is nice. I have two numbers. I'm going to include each of those in my t-chart, t-table. And I'm going to do 0 and 3. And I may choose on this one, like, because you might know about the parabola from transformation, so you can use that as an intuitive guide. But I might choose another number to plug in to kind of see what's happening with the parabola. So whether you choose one extra number or two extra numbers is kind of up to you. But I could choose either 1 or 2 to plug in there as well. So we'll just go ahead and evaluate each of those. That won't take very long. 0 minus 2, that's negative 2, squared is 4. 1 minus 2 is negative 1, squared is positive 1. 2 minus 2 is 0 squared, so that's 0. And then 3 minus 2 is 1, squared is 1. Okay, so I can kind of see there, like, that's going to be getting me the U shape. So it comes down to 0 and then turns around. Pay attention, again, to the interval. This works when x is equal to 0, so this is going to be a closed circle. And then when x is less than 3, so this should be open on the parabola or the quadratic graph. So plot those points, 0 left or right and 4 up is closed, 1 1 is closed, 2 0 is closed, and 3 1 is open. And so I just have this section of quadratic. Okay. So again, if you're familiar with transformations on a quadratic function, like you recognize x minus 2 quantity squared, that's going to be a quadratic or a parabola that is moved 2 to the right, you might already know where the vertex of your parabola is. So you can kind of use that to guide you as well. But a t-table is also a great tool. We have one more function to go to finish this piecewise function, and that is 3x minus 2. So I'm going to make a third t-table for that function. And I use that whenever x is greater than or equal to 3. So I'm going to go ahead and plug 3 in right there. When I do 3, 3 times 3 is 9, minus 2 is 7. And then do one more, so I kind of know where my next point is going to be. So 3 times 4 is 12, minus 2 is 10. And I can go ahead and plot those points. So 3, 7. And that's going to be a closed circle because this is or equals to, so this should be closed. And then 4, 10, so go 4 to the right and 10 up. Looks like I'm going a little bit off my graph here. And then I can extend the line up there. Now, on some occasions, you might have the situation where you have an open circle on one part of the piecewise function and then a closed circle at the exact same location. The closed circle will overlap and overtake, so then that will now be filled in, even though it was open for one part of the function. And so that could occur. To wrap things up just really quickly, you've got a couple practice problems over piecewise functions. They're on your gold sheet, and that's page 65, numbers 35 through 39. That's in addition to page 57, number 61 through 63, which go over average rate of change, which we did Friday in class. So thanks for watching this video. Go back, view any material that you need to see a second time, and we look forward to seeing you on Monday.